Now, it fairly could be said that chemists love notations. It's probably even better to say experienced chemists love their notations. New chemists have a love-hate relationship with their notations, and that's understandable, but it's one of the things I want to try to get you past here. We love notations because they add clarity to talking about difficult, complicated, and interconnected topics. And that's going to be a great setup for talking about electron configuration notations. Now, when we're trying to write out an electron configuration notation, the idea is that we're telling where all of those electrons could be on an atom in a very succinct fashion. So what we're going to do is we're going to look at our periodic table, see how many protons we have. We're then going to see if it's charged or not and adjust the number of protons into the number of electrons. And then we're going to start filling them up using our diagonal rules or our fast version of looking at the periodic table, whichever one we are most comfortable with. And we're going to write down for each of them the principal energy level, that's the n level from the quantum numbers. We're going to write down our type of an orbital. So if it's quantum number L equals 0, that would be an S. If it was L equals 1, that would be a p orbital. So there we are. And then we're going to put a superscript that tells how many electrons are actually in that orbital at this given time. Now, we're going to start with our 1s orbital, and we're going to keep adding pieces until we account for all of our electrons. Now, we definitely want to keep track of how many electrons we could have in each of those spots, too. For example, an s orbital will have a total of 2 electrons that fit. A p orbital, remember that you're going to have your orientation that's up and down. You're going to have your left-right. You're going to have your front to back as well. So you're going to have a total of 6 electrons that are going to be able to fit into a p orbital. You're going to have, let's see, 3, 5, 10 electrons that fit in a d orbital, and 14 electrons that fit in an f orbital. So 2, 6, so notice that it's 1 times 2, 3 times 2, 5 times 2, and then it'll be 7 times 2. Quick way to see how many electrons can fit in each of these. And we'll keep on adding until we've used up all the electrons that our atom or ion should have. So let's look at an example. Now, suppose we have chlorine. Take a second and look over at your periodic table. You really will want to have a periodic table open for the rest of this example. I'm not going to show the periodic table in the video, so please pause it now and pull up a periodic table to look at, either in hard copy in front of you or in a separate tab or window. Okay, so chlorine has 17 protons. It's neutral in this example, so it's going to have 17 electrons as well. We're going to follow our filling rules for our diagonal table. We have our 1s, our 2s, 2p. We'll have our 3s, 3p, 3d, 4s, 4p, 4d, and 4f. And that's probably as far down as I'm going to need to go for most things. I'm going to follow my diagonal. So my first one was my 1s, and it can hold 2 electrons. I'm at a total of 2. Next up, my 2s, I can fill in another 2 electrons. So now I'm at a total of 4 electrons. What you see me writing in below is not a formal notation, but it's not a bad bookkeeping approach either. We add in 6 electrons for our 2p. Remember, 6 electrons. So we have 6 electrons that we've added in. We're up to a total of 10 electrons placed. Next up on our filling chart, the 3s. So we'll have 3s. We can fit 2 more electrons in there. That gives me a total of 12 electrons. I keep looking back to see how many I have total, and that's going to be 17 electrons. I've got 5 more to place. I know that my next orbital, my 3p, is going to be able to hold 6. So I'm not going to end up filling up the p orbital, and that's fine. But I recognize that I can fit those last 5 in, so I'll put 5 there. I'm up to my 17. I've got all my electrons. That's what we're going to be doing whenever we do an electron configuration notation. And we'll be able to do this really quickly with a little bit of practice. Now, the other thing I'd like to point out, and here, please take a look at the periodic table after I describe this. Remember that our 1s orbital is going to look like helium, one of our noble gases. Having the 2s and 2p filled is going to make it look a lot like the next noble gas on our periodic table, neon. And so this whole segment is going to look like neon with, at least the electrons of neon. Of course, the nucleus is going to look different. It's going to look like the electrons of neon, but with an extra set of 7 electrons sitting on top. That's going to be something that's important, and I'll bring that up again in this same video in just a moment. Now, the reason that I was saying we're probably only going to care about those outermost electrons, keep in mind, if you have another atom coming close to it to interact, whether it's stealing electrons to make charged ions, or whether it's to start sharing electrons to make chemical bonds, either way, the ones that are going to be able to do that interaction are going to be your outermost electrons. So we're typically only going to talk about those, and we're going to refer to the outermost electrons as being our valence electrons. So we emphasize that by using our condensed notation. Now, with that, we're going to actually write the next lowest noble gas in brackets. You heard me do that verbally up here a little bit. So for example, up here for chlorine, I could go ahead and say, let's see, my previous noble gas was neon. So I'm going to go ahead and write neon in brackets. Then I'm going to write everything that happened after my last one was filled. So it'll be 3s2, 3p5. Now, with those transition metals, you'll have those d orbitals in there too, and they will be at one lower n level. You will also see that sometimes people will switch these two around, the d and the p. That's still fine. As long as you're filling them in the same order, you can write them in whatever order you'd like. But typically we're either going to write it in the same order we filled it, or we'll swap it so that our d orbital is the very last one. And there's different reasons for that that we'll talk about when we start making ions. But remember that either one of those two notations are completely equivalent and correct. Now let's take a look at another one. So this one's going to be selenium. Go ahead and pause and take a look at your periodic table now again. Okay, and you see that selenium is going to be atomic number 34. So we have 34 protons. It's got no charge on it. So 34 electrons as well. We've got 2, 4, 10, 12, 18, 20, 30, 34. And you can see that we're just following that diagonal again. We have our 1s, then we have our 2s, then our 2p, 3s, 3p, our 4s. We come back around and we do our 3d, and then we get to our 4p. So in our condensed notation, we have argon, 4s2, 3d10, 4p4. And like I mentioned before, it would also be completely equivalent for me to write argon 4s2, 4p4, 3d10. Notice we still filled it just like we did before. All we've done is swap around and keep the 4 s's together while having the 3d afterward. We could also have written it as argon 3d10, 4s2, 4p4. All of these are going to be completely equivalent. We make sure we still fill it in the original order, but then we're allowed to slide these pieces around to help emphasize different things to a reader.